tutorial, the next tutorial is up. I will email that out, or Nitin will email it out to the SATEX students that are taking this online. For the rest of you, it's on Moodle already. It's mostly Fourier class transforms. Then a bunch of things that I wanted to cover, but I won't have time in class. I've chucked it into the tutorial so you can work through it yourself. Today, I want to focus on a couple of things. Mostly exploring properties of the Laplace transform, derivatives. So this is the Laplace transform of derivatives as well as the derivative of Laplace transforms. I want to explore a convolution theorem. We're going to solve some differential equations. Time. Then I'll get to the inverse transform. Okay, so that's the plan. So let me remind you that the Laplace transform of some function f of t is the integral from 0 to infinity minus s t f of t. T is defined for us some function f(s), and there was conditions of this function f of t. Essentially, the conditions of the function f of t are required to make sure that this integral converges. The 2 points where we could have problems, one at t equals infinity and then one at t equals 0. I think this guy does not have a too strong singularity at that point, and I need it to be not dominant over the exponential at infinity. Once those two conditions are met, one is called exponential order, the singularity restriction, then I'm guaranteed that my integral will convert. And if my integral converges, then it's defined to me the Laplace transform of the function t, which we're going to call f of s. I said that one of the things that we want to use Laplace transforms for, which engineers use Laplace transforms for a lot, is solve differential equations, because that's what we do. And in order to do that, I would like to follow the same kind of strategy that we did using Fourier transform. I give you some differential equations subject to some boundary data, and you transform that boundary data, and you transform the differential equation. You get a differential equation with some boundary data in Fourier space. This is what we did in Fourier transform. And hopefully, the differential equation becomes something similar, like a Fourier equation. Solve that, and then you integrate it. Build out a small repository at this point of Laplace transforms, forward Laplace transforms. So we can look at a forward Laplace transform. We can look at a Laplace transform more or less either guess or manipulate it in various ways, like partial fraction decompositions, and read off then the inverse transforms. That's the strategy we're going to be using. But the first thing we need to do, if we're planning on using this to solve differential equations, is try to understand how the Laplace transform acts on derivatives. So to that end, suppose that I have a function suppose that all the necessary conditions on f t are met. sorry, this is grammatically stupid, horrible, but you know what I mean. Suppose that the necessary conditions on f of t and f prime of t are met. So that the Laplace transform of f of t exists and the Laplace transform of f prime of t exists. Then what we would like to know is what is the Laplace transform of the derivative of f in terms of the Laplace transform of f itself. I'm going to put this away. So let's directly apply the Laplace transform. This is the integral from 0 to infinity e to the minus s g df by dt. And we're integrating with respect to t. And this is exactly the form that we would need to integrate by parts. So if I integrate by parts, this is just e to the minus s t times f, which I have to evaluate between 0 and 30, minus, so the derivative of this guy, it pulls down the minus s, so it's 2 minuses, plus integral from 0 to infinity. Integral from 0 to infinity, differentiating this with respect to t gives me an s e to the minus s t f dt. I'm integrating with respect to t, so I can take the s out of that integral. This thing gets evaluated at 2 points. When t is infinity, the exponential will kill off any number. When t is 0, the exponential is 1, that's f evaluated at 0. Right? So this is just s times the integral from 0 to infinity of e to the minus s df dt, which is what we're calling the Laplace transform of f of t, minus f. Strictly speaking, when I say f of naught, implicit in this is the fact that I have to evaluate f by taking a limit, then I have to take a limit as I approach f, as I approach naught from the right. Okay. So that's the first derivative. The Laplace transform of the derivative of f prime is s times the Laplace transform of f minus f evaluated as 1. Similarly, or in fact, we're going to use this as an exercise. So, using mathematical induction, you can iterate to show that the Laplace transform of the nth derivative, I use standard notation for that, okay, of f is s to the nth power times the Laplace transform of f of t minus s to the n minus 1 times f of naught minus etc. all the way through to the n minus first derivative evaluated at naught. Okay. So this you just get by taking the Laplace transform of the k derivative and relating it to the Laplace transform of the k minus 1 and using this one. Okay. There's 2 points I would like to note about this. First is that similar to the Fourier transform, the Laplace transform converts differentiation into multiplication. So this way, ODEs get converted into algebraic equations. So it does what we were hoping it does. Unlike the Fourier transform, the initial conditions, f of naught, f prime of naught, etc., are baked into the derivative in the Laplace transform. Right? Like here. So once I take the Laplace transform of a function that might occur in a differential equation, its initial condition is going to appear in it as well. There's a second order derivative. I mean, if it's a second order differential equation, then f of naught and f prime of naught will appear. Okay. So I need the initial data in order to carry out the derivative. But that's not a bad thing. It's a good thing because it means that the initial data is treated automatically when I take the Laplace transform, unlike the Fourier transform where we have to do it separately. Okay, so there's two notes to make here. One, L acts. L converts derivatives to multiplication. Two, initial data is treated as this compare with Fourier transform. So this means that the Laplace transforms are automatically a good way to approach solving differential equations. Okay. As an example, and I'll use our go-to example of the harmonic oscillator here. Let's see how this would work in practice. Suppose we would like to solve the following differential equation. Okay, so the harmonic oscillator x of t satisfies the differential equation that m times the second derivative of x with respect to t plus k times x t equals 0. This is the simple harmonic oscillator, and this is the mass of the oscillator. And this is the oscillator's spring constant. This is the first position. Time t. And I would like to solve this subject to the following initial data. That is, I have this oscillator. Let's say it's 0 is here, and frictionless surface, M, that's K. And my initial data is that I displace this thing by some amount x naught and set it off from rest. Right, so the initial data is x at naught, so x naught, and dx by dt evaluated as naught, so x dot at naught, 0. So I start this thing off from position x naught and at rest. Then, if the Laplace transform of this capital X of t, I call little x of s, then if I Laplace transform this whole equation, so Laplace transform acting on m x double dot t plus Laplace transform on k x t is the Laplace transform of 0, which is 0. This is because of linearity. Tells me that this is equal to m times s squared little x of s minus m s times x at naught, which is just x naught, minus k times x of s, all that is equal to 0. This comes from the third term. This comes from applying the Laplace transform to the second derivative and using the initial condition that x at naught is naught and x dot at naught is x at naught is x naught and x dot at naught is 0. Right, so that's why I only have two terms here. Okay. Good. Any questions? Pretty happy with this? Yeah, good. So this is an algebraic equation in x of s, which I can solve. So x of s, I can just read off then, is x naught times s over s squared plus called omega naught squared, and as usual, omega naught is the natural frequency of this, and it is just k over m. So I divide 2 by m here, and I write this as omega naught squared. So that's the Fourier transform of the thing I want to find. But I recognize that this is s over s squared plus omega squared, which means that I can use this repository that we're building to say that x of t, which is just the inverse of the transform of x of s, is x naught cos of omega naught. So you can see what I mean when I say that the initial data is baked into the Laplace transform. I didn't need to transform the initial data. And solving this differential equation really just relied on us knowing what the inverse of this s over s squared plus omega squared is. So you'll do a couple more examples in your exercise. Questions?
The omega naught squared, where is it? Why is that squared? The k term is squared. Because s squared x of s minus x.
Yeah.
Minus k over it.
Yes.
Yes.
So omega naught squared is scale aware. So I could have, if I just left it like this, then I would have found the k over k. Okay. This natural frequency of the oscillator is defined as the square root of k over. Very good. So in your homework, you guys will consider two interesting variations that will really, bring out the power of this transform method. One is a damped oscillator, where there's a term proportional to the first derivative, and the other one is a damped forced oscillator, where there's a right-hand side as well. We will solve both of those cases in the tutorial. But let's continue enumerating these properties of the Laplace transform. So in particular, we've now just said what the transform of a derivative is. Let's see if we can write down what the derivative of a transform is. So df by ds. The original function. Okay. For this, we need to assume that f of t is at least piecewise continuous. And e to the minus st times ft is exponentially converted. Both of these conditions ensure that the Laplace transform of f of t is uniformly convergent. And I needed this condition to hold because I want to differentiate under the integral, and I want to be able to make sure that the derivative under the integral and the conditions for differentiating under the integral are met. The reason I want to differentiate under the integral is because I want to take the derivative of this function here, which requires differentiating this integral, which requires exchanging the order of derivatives and integration. F prime df by ds is then d by ds of the integral minus st f of t dt. And Leibniz said that as long as these conditions are met, I can take the derivative into the integral and it becomes a partial derivative. So that's the integral from 0 to d by ds st f t. This thing acts only on s inside the integrand, hence the partial derivative because the integrand is a function of s at t. When it acts on the s, it just pulls down a minus t, e to the minus st f of t. In other words, the derivative of the function is the Laplace transform of not f now, but minus t times f. So that's how the derivative of the transform reads in terms of the original function itself. The original transform. And as a quick calculation, I would like you to show that the nth derivative of f with respect to s is the Laplace transform of minus t to the n ft. as you would expect from the formula that we described. So one way of thinking of this is, just exploring properties of this thing, but I'm always trying to explore properties that will lead me to more transforms. Because at the back of my mind, I have the realization that I'm always trying to build up this repository, get as many forward transforms as I know how to do. That way, I don't have to do the inverse transform calibration. Okay. In particular, this differentiation can be used to generate more transforms. So use this to generate transforms. Follows. For example, since we know already that the Laplace transform of, let's say, e to the kt, the exponential, is simply 1 over s minus k, it follows then from this formula that I can work out what the Laplace transform of one of the moments of this exponential is. So the Laplace transform of, let's say, t e to the kt. It's the first moment of the exponential is just the derivative with respect to k of the Laplace transform of e to the kt. So this is just the derivative with respect to k of what I know this guy to be, which is 1 over s minus k with respect to k. I get 2 negative signs there, so this is just 1 over s minus k squared. Okay, more of this manipulation of known Laplace transforms to generate more Laplace transforms. Just following this logic, I would like to show 2 things. One is that the Laplace transform of t times cos kt is s squared minus k squared over s squared plus k squared whole squared, and the Laplace transform of t times sine kt is 2 k s over s squared plus k squared. Right, by the same logic, basically differentiating the space here, keeping track of minus. Any questions? Online? Okay. So let me do another example to make these concepts stick, A and B, because the differential equation that I would like to solve here has some practical interest. So let's solve following differential equation. X squared times s double prime of x plus x f prime of x plus x squared f x equals 0. Does that look familiar to anybody? I'm going to say no. Let me modify this a little bit, or maybe it'll make it. How about that? Okay. I'm going to stick with Kashi. You know, if you pick enough French mathematicians, you'll get it. Or you could like geographically diversify, go for Swiss Italian. German was English. All was French. Bernoulli was French. Oh, Italian. That's all. I know you're right. Bernoulli was also Swiss. The whole family of them. This is the nth order Bessel equation, whose solution is the nth order Bessel function. In particular, let's consider this equation, let's try to solve this equation, okay, for the case n equals 0. Solution is, of course, the 0th order Bessel function. J naught of x, which has a series representation, sum from s equals 0 to infinity minus 1 to the s over s factorial squared times x over 2 to the 2x. Okay, so this is some polynomial in x, and the particular polynomial it is one that has even powers of x with some horrible coefficients in front of it. And you'd say, well, why am I studying this if the solution is just this special function? Well, I would like to understand where this special function comes from. How do we get the series solution to that equation there with n equals 0? The first thing to note is that the initial condition that f of 0 be 1 says that we can divide 2 by x and solve instead the marginally simpler equation that x f double prime plus f prime plus x and f of x equals 0. And now I can transform this guy. And I'm going to assume that f prime of naught vanish. That's the first way. I need two conditions to solve this. So if I transform this, I'll find that the Laplace transform of x f of x plus Laplace transform of f prime plus the Laplace transform of x f x all equal to 0. Using what we've just learned, this is equal to minus f prime of s. Sorry. Not that. This is equal to minus f prime of s. The minus sign comes because I'm going to take the derivative with respect to.
This is minus of the.
Oh no, that's because the Laplace transform of the derivative is minus t. So the minus comes from here. So I want the Laplace, so basically the Laplace transform of minus t times f of t is f prime. So the Laplace transform of t f of t is minus f prime. That's where that minus comes. Okay.
Now I'm just looking at the previous set, the derivative of the constants of t, f, k, t. Are you missing a minus or there is something?
No. The Laplace transform, I wasn't using that formula, I'm using the principle that I was differentiating under the integral. So the Laplace transform of t to kt is d by dk of the Laplace transform of this, because I can take the dk into the integral, differentiate with respect to k, I'll pull out the t. Okay. Okay, so that's the first one. This guy here is equal to the Laplace transform of the derivative was just s f of s minus f of naught, which is 1. And the Laplace transform of this is equal to minus d by ds of the Laplace transform of f double prime. Now using that formula, which is equal to minus d by ds of s squared f of s minus s, which is equal to derivative with respect to s of this thing, which is minus 2s f minus s squared f prime of s plus 1. And I can put all of this together to get an equation for f of s. So in S space, in Laplace transform space, this differential equation becomes f prime df by ds equal to f prime times s squared plus 1 equal to minus s times f of s. Well, that's a separable equation in f. So I can separate the separable first order equation in f. So dx by f is minus s over s squared plus 1 yes. And if I integrate both sides, I'll find that d log f is equal to minus a half. Well, I can integrate this one. I integrate with respect to f on the left hand side, and integrate with respect to s on the right hand side. We will find that f s is equal to some constant over square root of s squared plus 1. This is, of course, the same as c over s times 1 plus 1 over s squared to the minus a half. And if I want to make contact with the series expansion of the Bessel function, which is what I want to do, then I can assume that s is greater than 1, so that this 1 over s squared is a small number. Taylor expand this time. And we'll get the series 1 minus 1 over 2s squared plus 1 times 3 over 2 squared times 2 factorial times s to the 4 minus etc. General term will be minus 1 and k term will be minus 1 to the k, 2k factorial over 2 to the k times k factorial times s to the 2k. Okay, let's just keep track of some of the combinatorics that comes with the Taylor expansion of this square root, inverse square root. Okay. And this is what f of s is. And each term there'll be a 1 over s cubed, there'll be a 1 over s term, there'll be a 1 over s cubed term, there'll be a 1 over s to the 5 term, etc. I can just invert term by term. What I've done previously, right? And so inverting term by term, we'll find that f of x is this constant c times sum from n equals 0 to 30 of minus 1 to n x 2n over 2 to the n and square. That with c equals 1 actually. C equals 1 is addition determined by this. I'm going to leave it there. F naught minus C equals 1. This makes f of x. As an added bonus, let me point out that this method of solving the differential equation to get the series representation for the Bessel function means that we automatically know what the Laplace transform of the zero Bessel function is. Because that's what f of s is equals 1. And that tells us that even though we don't have the Laplace transform, even though we don't have the zero Bessel function in closed form in terms of elementary functions, that's why I gave you a series representation, and otherwise you just write it as j of x. Its Laplace transform is in fact just 1 over the square root of s squared plus 1. Okay. So I want to do two more things before we call it a day. First is to do another quick calculation. And we have worked out for you here, what the derivative of the Laplace transform is. The derivative of the Laplace transform is just the Laplace transform of minus t times the function. I'd like you to show that the integral of the Laplace transform, so the integral from, let's say, s to infinity, is only a function of s, I mean, effectively an indefinite integral here. Dx is the Laplace transform of f of t, as you would expect, given that this is an integral f of t over t. If f of x is the Laplace transform of s is the Laplace transform of f. And then finally, for today anyway, I want to just convince you quickly that there is a version of the convolution theorem that exists for Laplace transform that is kind of useful when you're trying to solve the forced harmonic oscillator equation. Tutorial. So suppose I have two Laplace transforms. F1 is the Laplace transform of capital F1. Just dropping all the S and T dependencies here because it's obvious. And F2 the Laplace transform of F2 T. Then if I multiply these two together, F1 of S, F2 of S. This is the integral from 0 to infinity of e to the minus s x f of x dx 1, sorry, times integral from 0 to infinity of e to the minus s y, say f2 y